Hello, doctor. My name is SUNDONGXU, and today I'm presenting my analytics lab project titled DTDC Express Logistics Delay Analysis and Performance Prediction based on data mining. In the area of e-commerce, logistics is no longer just about moving goods from point A to point B. It is about precision, data, and fulfilling promise. My research focuses on using machine learning to solve a critical business problem for DTDC Express, predicting delays before they happen. Let's start with the context. The Indian logistics market is growing at a double-digit rate. However, this growth brings complexity. We face what I call the logistics paradox. As volume increases, efficiency often drops. Even a minor delay in a transit hub can cause a butterfly effect, leading to severe operational costs and irreversible damage to the brand's reputation. So, what is the core problem? Currently, DTDC operates on a reactive model. We call this post-disaster remediation. Management only reacts after a customer calls to a complaint about a delay. Despite having massive amounts of data, origin destination, which this data sits in silos. My goal is to change this, to shift from flexing problems to predicting risks by leveraging historical data. To achieve this shift, I established three main research objectives. One, identify the core factors that drive delays. Is it the mode of transport, or is it the weight of the payment? Two, build a classification model using random forest to predict the risk of delay, yes or no. Three, develop a regression model use this decision tree to predict the exact transit time in days. For the methodology, I follow the CRISP-DM standard. I utilized datasets covering approximately 2,500 shipping records. The process involved three critical steps. First, data cleaning. I used the Three Sigma rules to remove outliers, such as packages with unrealistic weight over 100 kilograms, which could skew our model. Second, future engineer. I create a new variable code to calculate the actual translate time and define delay status strictly based on the service level agreement. If a package arrived after the promised date, it is flagged as 1. Otherwise, it is 0. Third, ordering. I split the date into 80% for training and 20% for testing to ensure the real goals. Now, let's look at the data story. Figure 4.1 shows the distribution of our deliveries. 91.9% of shipments are on time. You might think that's a great score, but look at the roughly 8.1% are delayed. In high volume logistics, this 8.1% represents a pinpoint. These are the angry customers, the compensation collapse, and the lost business. Our model needs to catch this specific minority. Figure 4.2 reveals a surprising insight. When we compare transport modes, we see that express and surface have almost a similar warranty transit time of about 3 days. This is critical. Customers pay a premium for express, yet it doesn't offer a significant speed advantage over standard ground transport. This suggests the bottleneck isn't on the road or in the air. It is likely in the processing centers, which aligns with our theory of constraints. Moving on to the prediction results, I use the random forest classifier to predict whether a package would be delayed. Here is the confusion matrix on the text set. The model currently identified 1,801 on-time package. However, let's look at the areas. We have 148 negatives. These are delayed packages that the model missed. We only catch 3 actual delays. Why is it happening? This brings us to the critical concept I call the accuracy trap, which I will explain on the next slide. If you look at the first row of this table, the accuracy is 19.7%. Ideally, this looks excellent. However, because our data is imbalanced, the model can achieve 90% accuracy simply by guessing on time for everything. The real metric that matters for DTDC is recall for the delay class, which is only 8.07%. In our business context, a field negative is much more expensive than a field positive. A missed delay means a disappointed customer. Therefore, where the model is stable, this result highlights that relying solely on internal data is not enough to fully capture delay risks. We need more dynamic signals. So, what actually drives these delays? Figure 4.4 ranks the feature by importance. There are two major takeaways here. One, actual risk is king. It has an importance score for over 0.50. This validates my hypothesis. H2, heavier shipments are significantly more prone to delays. This is a physical bottleneck. Heavy goods likely require special loading equipment or waiting log for full truckload. 2. Origin city matters. Shipments from Tier 2 cities face higher risks. This indicates a structural bottleneck in inefficiency. Hub and spoke connectivities in smaller regions. Interactingly, transport mode ranks third. This confers that simple upgrading a page to air mode is less effective than solving the handling process for heavy goods. Beyond just predicting delay vs on time, I also used a decision tree regressor to predict the specific number of days required for delivery. The result is an RMS of 2.03 days. This means our prediction has a margin of error of about 2 days. Business implication: we should stop promising exact date like deliver in 3 days. Instead, we should use this RMSE to create a dynamic window. Estimated deliver in 3 to 5 days. This helps manage customer expectations effectively. Based on these findings, I propose 3 strategic recommendations for DTDC. 1. Early warning system. Deploy the random forest model into the booking system. An order with a predicted delay probability of over 70% should be flagged immediately. This allows operations team to intervene proactively. 2. Heavy goods track. Since weight is the number one constraint, we should establish a dedicated processing track for heavy parcels. This applies the zero of constraints by optimizing the bottleneck. We improve the flow of the entire network. 3. Communication strategy. Utilize the 2-day enroll margin to update SLAs. Proactively notify customers of potential delays before they call us. This turns a negative experience into a transparent one. To conclude, we successfully identified the weight and origin as the primary constraints. We achieved 90.7% accuracy in risk classification, providing a solid foundation for risk filtering. We validated that the strategic shift from reactive to predictive analytics is possible. However, the study has limitations. The law records that the internal data is not enough. Logistics is an open system. Future work to reach the next level of vision. We must integrate external variables specifically weather data and real-time traffic conditions. Rain and traffic jams are major keys of that our current dataset does not capture. This brings me to the end of my presentation. Thank you specifically to my supervisor, Dr. Jasmine, for her guidance. Thank you for listening.